Hello, doing physics again of electricity 3. Alright, let's start with the first question, which it says, it is a common practice in commercial installations to have a separate circuit for a refrigerator so no other appliance can trip the circuit breaker and shut off the fridge. However, Jill, Jill turns on a 1.5 kilowatt griller on the same circuit at the same time as a fridge that draws 10 amps when it starts. A 15 amp circuit breaker protects the fridge circuit. And part A of the question wants us to calculate the current drawn from the griller. So first we have to know that a normal Australian home takes 204, like the circuits have 240 volts. And then we know the griller takes 1,500 watts, and then we can use power equals V I 1500 equals 240 I, and to calculate I, oh my god, okay, I'm not that close at all. 6.25 amps. Okay, that's it for this question. For part B, it says, what's the resistance of the fridge as it starts up? Okay, so we have to find the resistance. So we need to use the V equals IR formula, and we know the V and the I because the I is given. So that becomes 240 equals the amps, which is 10 amps times R. And that makes it so that the resistance equals 24 omega. Okay, for part C, will the circuit breaker be activated when the fridge starts up? So the circuit breaker breaks based on the current. So we just have to add the two currents together. So it's 10 currents from the fridge starting up plus the 6.25 amps we just got from here of the griller. So we will get 16.25 amps. That is greater than 15 amps of the circuit breakers. So yes, circuit breaker will activate. All right, now let's move on. That's it for this question. Let's move on to the second question. Second question says, John is barefoot on a wet laundry floor. His right hand accidentally touches the frayed live 240-watt AC wire. John's body has a resistance of 4,400 omega to the ground. So he have a resistance of 4,400 to the ground. He has not protected his home with a residual current device, which means okay, there's no protection. And so for part A, what current will flow through him? So for part A, what current will flow through him? So we have the volts, we have the resistance. So use V equals IR. That is 240 equals current. We want to know the current. The resistance, which is for 4,400, and that makes us that I equals 240 divided by 0.0545455. All right, 5 with this amps. Okay, and for part B, it says, before part B, there's new information of how Carmen tries to rescue John without first switching off the power. She grabs his left wrist. Carmen has a resistance of 8,000 omega, and the resistance of John's John's body between the wire and his left wrist is 400 omega. Wait, the resistance of John's body between the wire and his left wrist. The left wrist is 400 omega. Okay. Oh wait, let me think about this. Okay. And we have to, for part B, we have to figure out does the current through John's heart increase, decrease, or stay the same? Okay, so let's draw a diagram. Yeah, let's see. This is the wire, and John touches it with his right hand, and well, they're all connected to ground, so we'll have, oh my god, we'll have ground, and John can go through here, and it can go through here, and it goes to Carmen, and then it goes to ground again. Okay. So first, John is 4 omega, 8,000 omega. So is this circuit a series or it is a parallel circuit because Carmen just adds herself in. Is it him? Yeah, it's her. Okay, so but it says the resistance of John's body between the wire and his left wrist is 400. Okay. So there to there is 400, but there through here is 4,400. How does that work? Let's think of John as a resistor. Okay, so John, if it passed through here, that's 400. But if it passed through here, that's just 400. Oh, 400. So that means that the current can either take the path of straight to the ground, 4,400, or takes another path which is through Carmen and also through his left arm. Okay, yeah, no, I get that. I get that now. So we can do part B now. Part B said, does the current through John's heart increase, decrease, or stay the same? So basically, the wire will still go through the exact same path through there. So, no, it would not. It would not change. It would not affect his heart as because a new path is added. A new path is added. Does that affect John? That does not affect John because I mean this depends. It depends on if John's body between the wire and his left wrist goes through his heart. It might just go through his shoulders. So this question's bad. That's the conclusion that the question's bad. Okay. So let's just assume it doesn't go through his heart. So it's either through John straight down to the ground, or it takes another path. And because of that, because of that, it should be the same. We're just gonna say it's the same. So, current through his heart stays the same. Or it can increase. It can never decrease because you add more things, so more current goes through. If you add more resistance, the current will be. Actually, it shouldn't, but it does. So, oh well. Now part C. Part C asks us what current will flow through Carmen. Carmen. Herm. So basically, we'll just calculate what current. So V equals IR. We know that it is a parallel circuit, so the voltage will be the same, so it'll be 240, and resistance will be 8400, and R is there. Actually, I is there. I equals 240 divided by 8400. That equals 0. 0.0286 amps. And we'll say why does the path through John's body count? It's because we can calculate that as one component in the circuit, and even if the left arm is different, because they're in a series, they should have, because the arm and column is in a series circuit, these two should have the exact same amps. So this must be right. And for part D, we want to calculate what should Carmen have done. So Carmen should have she should have she should have switched the power off. Switched power off, or detach a live wire from John with non-conductive materials first. It's valid. And for part E, they ask, explain why the fuse in the house circuit has no protection against electrocution. Well, this is because fuse is not used to to stop electrocution. Fuse only activate and breaks a circuit when a short circuit happens, and this is because that a fuse let me write this happens. This is because the fuse is basically just a piece of wire, but it breaks when it's at higher temperatures, like it melts and then stops contact. Because that when a short circuit, the resistance like basically zero, and then like the current will be really high, and it creates a lot of temperature, and then it'll melt things and breaks the circuit, break the wires. So the fuse protects that. But when human connect connects circuit or to ground, they have their own resistance not always short circuit allowing making it so that the fuse might will not help. Will not help. Okay, let's redo part B, because I'm suspecting that it might be increased. Okay, so it's valid saying that the heart stays the same. It's also pretty valid saying that the amplitude will the current will increase, because let's just try it. So we use the parallel circuit resistance formula. So 1 R total equals 1 over R1 plus 1 over R2, which equals to 1 over 4,400 plus 1 over 8,400. And that equals to, let's do that, 4,400, 1 over 8,400. That equals to 0.00346, and RT will equals to 1 divide that, which equals to 2887.5, and V equals IR and 2, that means 240 equals, well, I 2887.5, which means I equals 240 divided by that, which means that equals 0.083 amps, which is bigger than 0.0545, and that means, oh my god, stop, that means current can increase to, oh well, the question's designed weirdly. I think they both are valid, so oh well, that's it for the questions. Bye bye.